Okay, so there was a little mistake in this. Totally slipped past me. I'm sorry about that. But let's get this pogo stick problem straight. It's a nice problem. Uh, Initially, we said that there was PES. Now, where is initially? Initially must be here at position A then. So we're going to come over here, position A. Okay, good with that. Finally, maybe an easy one would be position C. We'll jump over here. We'll say equals PE, just gravitational. The problem is we actually missed something. What we missed, we'll zoom in over here. Here's what we missed. The problem told us to call this location, right? Let me flip this arrow around. This location right here along this height level, this was 0. This was energy equal to 0. That is our 0 height. Height equal to 0. What we didn't see in this little teeny picture and didn't even think about is that actually at point A, position A, the jumper is below the 0 line. So in fact, there is also PE initially. So in solving for the total energy, you can do either side. We could do 1/2 kx squared plus mgh. And of course, that's going to equal your mgh at position C. However, when we run these numbers, and so let's do that right here to make sure that we're actually talking about the same thing. This is 1/2 times 1,000 times negative 0.100 squared. We already found that to be 110, I believe. Plus, there's an mg here. Let me move this over so the equal sign kind of lines up. Plus the mgh. So in this case, let's see, the child is, combined mass is 28 kilograms. 28 times 9.8 times, there's a height here. That height actually is negative 0.100. Aha! That then has to equal the mgh at the end, but we're not really worried about that. The total energy then is this. It is not just 110. It is now 110 plus 28 times 9.8 times 0.1. I'll put that in the calculator to get it just right. So we're going to subtract 27.4, which is going to give us then 82.6. So that's a significant difference. That's our total energy. Okay, so part A is 82.6 joules, not 110. So notice here, if you do get a pogo stick question, that little height difference here at the beginning, you call the equilibrium position of the spring here, we'll call that 0. That little loss of height actually contributes. So we're starting a little lower, which means we have a little less PE, which means total energy is a little lower. Okay, then we have to determine x2. Well, x2 is the height from this calculation over here. So that actually is not difficult to do. We can continue our problem up here. That one just would be, we don't need bold anymore. It would just be the same. 28 times 9.8 times height. Height here is x2. And so if you solve for the height, let's see, 82.6. Make sure I didn't mess that up. 110 minus 27.4. Yeah. Divided by 28, divided by 9.8. We're talking about 0.30. 0.301 maybe meters. Yes, this meters. So that actually is the height. We based it prior on the 110, so it's actually going to be a little lower. This one we did the correct way, so no worries about that. Part 2 we did correctly. Part 1 we did not. So you got to watch out for that. Calculate the speed of the child at x equals 0. That one we also did correctly. Now our numbers, had we run them, would have been off because we have to do this little setup again. Now we could do it. Initial is at A and final is at B. And so it's just KE, and we know all this business over here already. So now it's just 1/2 times 28 times V squared. This, by the way, is 1/2 mv squared. It's not mgh anymore. It's a KE at position B. Position B only has KE, by the way, because it has no height. That one is defined at no height. And because the spring is at its equilibrium length, so there's no PES. So here, when you solve for V, let's see, 82.6 times 2, divide 28, square root 2.43 meters per second. That one we set up correctly. We just didn't run the numbers. Had we run the numbers, we would have gotten a different number because our total energy was not set up right. So part A was a problem. Part B and C, good to go. Now part D is actually a nice question. E is easy, but D is a nice question. The value for which the value of x for which the kinetic energy is maximum. Now that's a little bit of a tricky question because we ignored the x1 in part A. That's why we're looking here and saying, oh, well, that's got to be the spot. But it's tricky. So let's check it out. Let's draw a free body diagram for part D. The free body diagram looks like this. Here's the jumper. Now, he's got 3 forces acting on him. He's going to have G, and, sorry, 2 forces. And Fs. So the Pogo stick's pushing on him, and gravity's pulling down on him. These two, depending on which one is bigger, he will continue to accelerate in a direction. Now, excuse me. If at this point here, let's draw this out. His FG is constant, so we can put a little FG arrow on it. FG right here. FG is constant. That's his body weight. So that's the same whether it's here, whether it's here, whether it's here. That doesn't matter. The force of the spring, however, is not constant. When the spring is compressed, notice what happens is it pushes him up. The only way that can happen is if the force of the spring is bigger. Now, that's the only way he's going to accelerate upward, which he does. So he's going to have a net force upward. At this point, he has the spring has gone to its equilibrium position. There is no force upward. So at this point, he actually is going to be accelerating down. However, he has speed at this point, so even though he's accelerating down, it's like throwing a ball up in the air. He has speed upward, acceleration downward. He'll still rise, but he's going to slow down, hit a peak, and come back down. So let's continue over here. There is a transition where the Fs gets a little smaller, a little smaller, a little smaller, somewhere between here and here. So if we saw him like when he wasn't all the way sprung up, but part of the way sprung up, maybe the Fs would be like a little less, and Fg would still be the same. But there comes a point where the Fs exactly will match the Fg. That is the point where there is no acceleration. So here he's accelerating up. Here he's got a smaller acceleration up. Here he's got no acceleration. Then he's accelerating down. As long as you're accelerating up, you are still gaining speed in this case. So what we're looking for is actually this spot right here. We're looking for the point that the Fs and the Fg exactly match each other. That's the point where the acceleration has gone to 0. That is where he will have the maximum kinetic energy, the maximum speed. So we actually need this picture right here. When is this true? When is Fs equal to Fg? Oop. Well, that's actually the location we want for max speed. Fs has to be Fg. And so then we can just do, well, Kx equals mg. As it turns out, we know K, we know M, we know G. So let me shrink this up so we can actually fit it into this little box over here. So if we run our numbers here, we know that K is, we say 22,000. X we don't know, equals 9.8 times 28. Obviously, X is going to come out pretty small. X equals, see here, 9.8 times 28 divided by 22,000 is 0.012, 0.012 meters. Now notice this is 0.1, this is 0.012 meters. So we're at 10 centimeters here, and we're actually going to be at 1.2 centimeters here. That is actually the answer. Keep in mind, by the way, this is meters, and the question over here is written in millimeters. So it's 0.012 meters, which is 1.2 centimeters, which is 12 millimeters. Actually, 12 meters, it's going to be negative 12 millimeters because it's below that 0 still. And then finally, determine the child's maximum upward speed. Well, now that we know where it happens, this one is, like, again, not hard to do, but it's kind of the chunkiest one to have to fill in. So let's do it. The initial we'll do from A, and the final will be, now let's call it X. Let's call it V max. So this is happening. This location, this V max location, is like here, somewhere between A and D. That's that V max where he's part of the way up, but not all the way up yet. And so at A, we knew it was PES and PE, and we went through all this business here. At V max, here, this is where it gets chunky. There's still PES plus there's actually some height below 0. So there's PE and there's KE. Oh boy, this one's going to be a little messy. That's okay though. So we already know this side is 82.6. That's convenient. This side, we have 1/2 KX squared plus MGH plus 1/2 MV squared, and this V is actually what we're looking to solve. All right, let's start running some numbers here. So 1/2 K was 22. Come on. There you go. Subscript, superscript, subscript, superscript. 22,000 times 0.012 meters squared. Technically, it's negative, but it's going to be squared, so it doesn't matter anyway. However, the negative is going to matter here, plus 28 times 9.8 times negative 0.012 plus 1/2, what's that over here? 28v squared. Oh my goodness, look at this mess. Anyway, very doable here. Half of 22,000 is 11,000, and this one's going to kill at 0.012 times 0.012 times 11,000 gives you 1.58 plus, let's see, 0.012 times 9.8 times 28, negative 3.29 plus 14v squared. And of course, you're welcome to shut off the video at this point because easy enough to run your numbers, but I'll take it to completion for you if you feel like watching. 82.6, 8, and add 3.29. We're going to divide by 14. We're going to square root, and we're going to get 2.45. All right, a little bit faster. So if you weren't careful with sig figs, that would probably be the same, but as part C. But anyway, that's what it is. So the pogo stick problem, beware. Most importantly, in the beginning here, it does have height below 0. Okay, so that should be about